Assume that we have a Poisson point process, and then we give this Poisson point process to a differentiator. A differentiator is an LTI system with impulse response of this one, and we calculated this autocorrelation and cross correlation. Now, if we give a Poisson process and give it to a differentiator, so we get Poisson pulses. So Poisson process, if this is time 0, let's say you have first point here, and then second point here, and third point here, fourth point, fifth point. So here you get 1, here you get 2, here you get 3, etc. So if you calculate d to dt of x of t, then what you get, this is x of t, the output will be 0 everywhere except at the points that you have a jump. So you get a delta of, let's say, t minus the location of the first one, t1. And then you get, so this will become summation of delta t minus ti when I equal to 1 to plus infinity, when the ti is the location of point processes. And then we call this one Poisson impulses. So one practical example of that is when your brain wants to control, let's say this is muscle of your hand and this is your nerve. So your brain transmits Poisson impulses. So it cannot generate delta pulses, but it generates some RC circuit, which is roughly like Poisson impulses. And then they in time, they are entirely random, but the traffic rate represents the amount of the force that the muscle is producing. So the expected value of x of t, if you remember in previous chapter, was equal to lambda, which is the traffic rate, times t. Now, if this random process y of t, if you calculate derivative of these, the expected value of y of t becomes derivative of that is going to be lambda. So the average, the expected value, or the mean of the impulses is proportional with your traffic rate. So if your brain increases the traffic rate, the average of the signal increases. Moreover, we have seen that the autocorrelation of the input with the input is equal to this one. So now if you calculate r, y of t1 and t2, I have to calculate one times derivative with respect to t1, another derivative with respect to t2, or whatever I have here. Now, if I calculate this one times derivative with respect to t1, one time with respect to t2, one time with respect to t1, the first one disappear, another time the second one. So this will become lambda 2, and derivative of this one, let's say t1 is smaller than t2, so if you get the derivative with respect to t2, it becomes 0. So in any case, this second term will disappear, one of them. So the autocorrelation of the output is proportional with your traffic rate to the power of 2. And you see that this is constant, this is constant. So therefore, the Poisson impulses is wide sense stationary. So so you could calculate this one and then see that you get lambda 2 plus t1 minus 2. So this is the autocorrelation. So this is like the DC term, the constant energy of this one, and then this one has. So by denoting t1 minus t2 as 2, you see that the autocorrelation of the output will become lambda 2 plus delta 2. Remember that this delta is derivative of the unit step function.